Hello, my name is Zahin Arfan Bin Zafudin, a final year student. My supervisors, TS Dr. Muhammad Hafiz Mawano and TS Dr. Ahmad Hussein Abdul Hamid, as Senior Lecturer, Faculty of Mechanical Engineering, UiTM Shah Alam. The final year project is titled Performance Prediction of a 3-spool High Bypass Ratio Turbofan Engine. Going to the background of the study, aircraft emissions significantly contribute to global warming and environmental degradation. A major way to reduce these emissions is by designing engines with a lower specific fuel consumption or SFC, which directly improves efficiency. However, actual flight testing of engines is costly and complex, requiring operational aircraft. Laboratory testing, such as using an airborne test rig, is also time-consuming due to extensive setup requirements. This creates a need for a reliable preliminary prediction tool for engine performance before committing to physical testing. In this project, I developed a computational interface capable of predicting specific thrust and SFC based on the Rolls-Royce Trent 100, a 3-spool high-bypass turbofan engine. The study focuses on 4 key parameters: bypass ratio, overall pressure ratio, fan pressure ratio, and turbine entry temperature within realistic operational ranges. Results show close alignment with actual gas turbine data, making this tool both accurate and highly beneficial for engine design optimization and sustainable aviation practices. Next is the theories and educational principle. This study is grounded in basic propulsion theory and the thermodynamics of gas turbines. By applying continuity, energy, and momentum equations across 12 thermodynamic stations of a turbofan, from intake, compressors, combustion chamber, turbines, missing, and exhaust, the tool simulates real engine cycles. The relationships between BPR, OPR, FPR, and TET with performance outputs are well established in literature, such as BPR effects, thrust and fuel efficiency balance. OPR improves thermal efficiency but may impact thrust depending on design. FPR influences airflow and pressure across the fan stage. And lastly is the TET is directly linked to power output and thrust potential. For the results, for findings, from validation, the model showed the highest accuracy at FPR 1.5, so this value was used for main analysis. Key results include: number 1, increasing OPR significantly reduced SFC with minimal thrust loss. Number 2, higher BPR improved SFC but lowered thrust, indicating a trade-off. Number 3, increasing TET increased thrust by 3.54% with only a 2.12% rise in SFC. And number 4, at high altitudes, thrust increased by 5.66%, while SFC rose just 0.28% at 10,000 meters, showing better efficiency in thinner air or higher altitudes. The implications: this tool allows UiTM to perform independent, accurate performance studies without relying on costly external software or experimental setups. It also supports sustainable aviation by enabling faster optimization of fuel-efficient engine designs. Next, about the unique about the research. What makes this project unique is it is locally developed, fully customizable interface for a 3-spool turbofan analysis, something rarely available in Malaysian universities. It is a low-cost alternative to commercial tools like TurboMatch. Here we have the interface. On the first page, users input altitude, pressure entry, and temperature entry. These are linked to the US standard atmosphere properties to ensure realistic conditions. And for the demonstration, let's say we use the altitude of 5,000 meters above ground. In the results section, the interface calculates performance for different BPRs with sub-calculations across OPR values of 15, 20, and 25. For each OPR, it tests TET values from 1650 to 1800 Kelvin, and within each TET, FPR values from 1.5 to 2.0. The final outputs are specific thrust and SFC for each parameter combination. And lastly, the interface generates graphical summaries that clearly show how each parameter affects performance at specific altitudes.